Okay, I think it's recording now. All right, so I'm just going to jump back into the reactions of alkynes now. All right. Okay, so as we got to what did we talk about last time? We showed like how to make alkynes by a couple different methods. The big one was the alkynyl anions, the things that we use a base and take off the proton from the end of an alkyne, and then we can go attack things. But now we're more onto the reactions of alkynes, and one of those reactions is reduction of alkynes, all right? And we mentioned the three ways that you can reduce alkynes last time. There's the full reduction. I'll show that in a second. But that completely reduces an alkyne from a triple bond to a single bond. And that uses H2, palladium, and carbon. Palladium, right, it's a metal. And we use palladium to reduce things a lot. And then we have something called a partial reduction. A partial reduction that makes a cis alkene, right? A cis alkene is where the things are on the same side. And that uses something called H2 Lindlar. I'll tell you what Lindlar is. It's Lindlar. Okay, Lindlar, Lindlar. And that's a partial reduction. It goes from a alkyne to an alkene. We also have a third one, which is a partial reduction that makes a transalkene, and that uses something else, sodium and ammonia, Na and NH3. Okay, and the behavior is kind of dictated by the mechanism of these reactions. So we'll talk a little bit about the mechanisms of them also. All right, good. So let's, I'll just show the full reduction real quick, then I'll jump into the partial reductions. So the full reduction, let me open the chat too. The full reduction, I'll just show an example of it. Okay, so it's alkyne. And what are the reagents for the full reduction? Well, it's H2 palladium on carbon. H2 palladium on carbon. Does anybody know what that means, PD/C? Palladium's a metal. Carbon is essentially charcoal in this case. So it's basically the metal is absorbed into charcoal. Okay, how many carbons will we have in the end? We have 1, 2, 3, 4, 5, 6 carbons in. Should have 6 carbons out. And it just makes hexane, right? Okay. You can also use platinum, PT over C, palladium, platinum. Okay, the mechanism of this is really similar to alkene reductions. And I'm not really going to go into it. It's not that exciting. You don't have to know it. But it's essentially the hydrogen gets absorbed onto palladium or platinum, and then it just gets delivered to reduce the alkyne. It'll be kind of like the Lindlar, which I'm going to show in a second, the Lindlar one. So that's the full reduction. So, but this is not a mechanism we really care about. It's not that exciting. Okay, let's go into the Lindlar now, the one that makes a cis alkene. Okay. I'm going to go to a new page, and we're on number 6, reduction of alkynes. So we're going to do the partial reduction via Lindlar, H2 Lindlar. Okay, and so what is H2 Lindlar and what does it do? So I'll draw the reaction and we'll talk about what is in the Lindlar mixture. But let's just do our same old 6-carbon alkyne. 1, 2, 3, 4, 5, 6. And what is it? What's the product? So it's H2 Lindlar. Catalyst. So what that makes is a cis alkene of this. So it's going to be 6 carbons. So cis, of course, means that the hydrogens are on one side, the carbon substituents are on the other side. Okay, and what is Lindlar? Not something you have to really care about or know, but it's a formulation of stuff. Palladium, calcium carbonate complex. So it's a special kind of palladium that's complex to this calcium carbonate stuff. Also lead acetate. And also something called quinoline. You can Wikipedia the structure of it. But it's essentially there's a weird mixture that is a little less active, a little bit less active than normal palladium, and that's why it kind of stops halfway from the alkyne to the alkene. I guess Lindlar was probably the person that discovered it and put their name on the catalyst, and that's what happens when you discover something kind of famous. So you guys need to discover something famous and you'll get your name on it. All right, so what's the mechanism roughly? And why is it cis? Why cis? That is explained by the mechanism, and I'll just summarize the mechanism of this. It's roughly the same as just a normal palladium catalyzed reduction. All right, so the idea is you got your special catalyst, the Lindlar. This is the Lindlar. The Lindlar catalyst. And what you got then is you have your H2, is a gas. And essentially, the hydrogen gets absorbed onto the catalyst. So the catalyst is kind of a metal surface. And so the way to do that is 2 arrows. I draw my H2 and I draw my metal, the Lindlar catalyst. And then I have like an arrow go this way, an arrow go that way. And what is the result of that? The result of that, of course, is now I have the surface of the catalyst with my H2 absorbed onto it. And then I'm going to draw my a random alkyne. So C, triple bond C. This is a little different than the alkyne above. Same idea. And now you can see that this is kind of can line up in a way. Draw some little dots, which is where the bonds are going to form. And we're going to do the same kind of thing now, where the triple bond will attach to the H2. So double arrow, arrow, arrow. And now H2 has been delivered to the alkyne. Now you got your catalyst back, and you got your cis alkene. Okay, I should draw that a little nicer. Cool. Okay, so this is a cis alkene, right? Cis alkene. The name of the addition, because this type of addition where things get added on the same side, it has a name also. The product is a cis alkene. Does anybody know what the name of the addition is? It's either syn or anti. Anti is obviously going to be the opposite. But this is called a syn addition. Syn, S-Y-N addition. It's a syn addition that gives rise to a cis alkene. So this just kind of describes the stereochemistry of the addition. You probably learned this in the alkene chapter too, the syn addition versus anti-addition. But anyway, that's it. That's the mechanism of why do you get a cis alkene using H2 Lindelar. All right, cool. That's a nice simple mechanism for us. So then the other one is the partial reduction via sodium ammonia, NaNH3. This is not the same as, remember the base we were using a bunch in this chapter, NaNH2, right? That's different. NaNH2 is a base. It's Na plus, NH2 minus. This is Na dot, like sodium radical metal, so metallic sodium, and NH3, which is actually a gas at room temp. So you can, how do we liquefy NH3? Because is a gas really a useful like solvent? A gas would not be very useful, but we can cool this down to like negative 100 degrees, and now it becomes a liquid. So we can just do this reaction at super low temperature. And the partial reduction will give us this partial reduction will give us a trans product instead of a cis product. Okay, cool. All right, so let's just show an example of this, and I'll show the mechanism. I hope you guys are drawing your alkynes this way, sort of linear-like, right? Don't draw the bent alkynes that I talked about last time. It should look like a kind of a linear-looking structure here. Okay, and so it's Na dot, sodium metal, which is actually kind of like a free radical. It's got that free electron. What's the trans product? If we do a partial reduction of this alkyne, it looks like that. It's trans, right? It's a partial reduction to give a trans alkene. Okay, so the mechanism of this is a little more complicated, but we can do it. One of the things that radicals do, because the sodium kind of acts like a radical, is they can add to double and triple bonds, like an alkyne. And so when we do that, what kind of arrows do we use? We don't use normal arrows. You know, we use those things called fishhook arrows. Remember fishhooks? Fishhook arrow. These kind of arrows that don't have the, you know, this versus... You learned about this in early organic 1, fishhooks. It's a radical arrow, as opposed to a normal arrow, which has like a, you know, a full arrow. These are 2 electron arrows. These are called 1 electron arrows. But anyway, radicals use fishhooks. Okay, so how am I going to do this? It's just going to attach to the alkyne, and I'm going to draw that. So kind of like a fishhook. Fishhook. I'm going to draw another fishhook from the alkyne. Okay, those are going to connect. And then we're going to draw a third fishhook onto the second carbon. So basically this is attaching, and it's going to create a new radical on the carbon. All right, so what does that do? What does that look like? Kind of like, now you got your sodium attached, right? And a radical. It's an alkene radical, okay? And this thing is essentially equivalent to, that's not an alkyne, that's an equivalent. So when I draw, this is not a triple bond, this just means this is equivalent to what I'm going to draw over here. remember, like from organic one, when we're attached to a magnesium bromide or lithium, we don't have to draw a covalent bond. We can draw an ionic bond, right? And it's essentially, or maybe I should use the equivalent, like the two squigglies, because it's essentially equivalent. This thing's essentially equivalent to a different molecule. Radical, carbon, so a negative and a plus. It's kind of like an ionic complex. So we have I'll draw a C for carbon here. So I'm drawing both of my carbons of the alkene. It's a carbon with a dot, right? And the other carbon has got an ethyl group, and it's also got a dot dot negative and an Na plus. So let's draw the plus sign nice and clearly. What's that called? It's an ionic complex, right? It's an ionic complex between C dot dot minus and Na plus, right? Okay, cool. And if you remember something about these ionic carbons, they are super reactive. It's a base, right? It's a strong base. And you have a proton source, ammonia, so this dot dot minus is actually going to grab a proton off ammonia. And that's going to give one of your H's, right? Okay, so I'm going to just use it, circle on pair, attack NH3, and basically grab a proton, right? Grab a proton. What does that make? Ah, you got your first proton. I'm going to draw each of these carbons now as a C, just to be clear. All right. Cool. Okay, so then the next step is a sodium dot. Sodium dot is now just going to attach to that carbon with the radical. So it's, how do we do that? It's going to be two fish hooks. So fish hook, fish hook. So carbon dot, sodium dot, make a bond. And what is that going to make? Something like this, all right? Now the stereochemistry is a little mobile right now. So it's not exactly like a cis and trans type thing. But now that's a negative charge, right? And then you probably got a sodium hanging around. Okay, so now you have this kind of intermediate with a carbanion, a C dot dot minus, and it sees another ammonia, H3N, and it does the same exact thing. C minus grabs the proton, kicks electrons onto nitrogen, and the end result is you get a transalkene. Now it may flip over. I drew it kind of flipped over here. No big deal. That's all irrelevant. The big thing though is that since you have multiple steps in this mechanism, it wants to make the most stable product, and that happens to be trans. That's why it's trans, okay? The reason it's trans is because you have a multi-step mechanism that gives rise to the most stable product. The Lindlar thing was not really multi-step. It was a single step, and that's why it got added on the same side and you got the cis product. That's roughly why we get a trans product here and a cis product in the Lindlar. Okay, cool. So we can say that in words. Say, why trans? Why is it trans? Radical intermediates. You have these radical intermediates, they can equilibrate to give most stable geometry. And that's trans. Trans is more stable than cis, right? The cis reaction, the Lindlar one that we just saw, is really just a single step, no equilibration. No single step, no equilibration, and that it just gives you the cis product. All right. So that's it in a nutshell. Why Lindlar gives cis and trans gives the sodium ammonia, NH3, gives you the trans product. All right. So we're still on that reduction thing. Let's just show the 3 examples one more time, summarize. H2 palladium on carbon does what? H2 Lindlar does what? Sodium ammonia does what? Okay, so H2 palladium on carbon does a double reduction. It goes from triple bond down to single bond. One, two, three, 4 carbons hanging off. H2 Lindlar gives a cis product. Sodium ammonia gives a trans product. All right, that's a nice summary, right? Here's a synthesis problem for you to attempt or ask me about in office hours. Say I got an alkene, and I want you to make me this product. Anybody want to give me some suggestions on how I might do this? Maybe we'll try it. I gotta do this kind of quickly. Any ideas about this? Because you might think, oh, well, all we got to do is attach this thing, right? That's what it looks like. But if you remember your alkene stuff, there's no way to just magically attach stuff to an alkene like this. This would be an impossible synthesis. But we do know how to convert an alkene to an alkyne, right? Last lecture. We also know once you got an alkyne, it's easy to attach stuff like this thing, right? That's a squiggly line. We know how to attach stuff. And we also know that once we have an alkyne, we know how to reduce it to make it. Is this cis or trans? This looks like a cis, right? H2 Lindlar, right? So we should be able to do a 3-step process. I'll give you the hints. You can fill them in. The details. So we can convert this into an alkyne. Once you get an alkyne, we can do a certain thing to attach that 3-carbon piece. And once you got that, how do you turn this alkyne back into a cis-alkene? A cis-alkene via which reaction? The Lindlar, right? So the last step's H2 Lindlar. But you should be able to fill in the details for this, which is last lecture, and also this, which is also last lecture. Does anybody know? Just think about the piece we're going to attach. How many carbons is it? It's how many carbons? Somebody should probably be able to count how many carbons there will be. Extra carbons. 3 carbons. And is it going to be a ketone, aldehyde, or epoxide? Ketone, aldehyde, or epoxide? Based on where the OH is and where the squiggly is it a ketone, aldehyde, or epoxide? There's my squiggly again. Ketone, aldehyde, or epoxide? It's the squiggly is 1 away from the OH, so it's, yep, somebody said it, epoxide since 1 away, that's right. So it's a 3-carbon epoxide. So what's step 2? It's going to be a 3-carbon epoxide. That's your epoxide. I'll do step 3 is water. I'll let you fill in all the other steps, all right? That was a cool synthesis problem. Very exam-like for the exam 1. Okay, all right, so you can fill in the rest of the details here later or whenever. Cool, nice. Okay, we're done with 6, now we're on 7. These are addition reactions to alkynes. Addition reactions to alkynes. This is kind of like, or similar to chapter 12 in some ways. Remember chapter 12? That was the end of organic 1. That was the alkene chapter. Okay, so there's some similarities. I'm going to review just a couple of the reactions from chapter 12 in very minimal detail, just to get it fresh on our mind. So these are some things from, recall that alkenes react with electrophiles. They react with electrophiles. Alkenes react E plus for electrophiles. So that was a key theme from chapter 12, that alkenes react with electrophiles. So a couple of the examples are, like if I had an alkene and I reacted with HBr, this was the easiest reaction from chapter 12. Your product was that. So essentially the H goes on the end and the Br goes in the middle. Is this Markovnikov or anti-Markovnikov? Because that was a concept from the alkene chapter. It's like where the thing is getting added to the more substituted position, and thus it is not anti-Markovnikov, it is normal Markovnikov. Markovnikov. Remember Markovnikov's rule? Okay, so that's a Markovnikov product because the Br goes to the more substituted side. Does anybody remember the mechanism of this? It's not a hard mechanism. It's actually the easiest one from chapter 12. Essentially, like I said, alkenes react with electrophiles. So HBr is an electrophile. Essentially, the alkene attacks H, kicks off Br. Okay, so I'm not showing the full mechanism just to save time. But yeah, of course, you get a carbocation, right? A carbocation. And then Br minus attacks that. Okay, so to be brief, I'm going to just continue. But that's like a easy chapter 12 reaction. Okay, so what about from chapter 12? The reason I'm doing this is because it's going to be similar to alkynes. Remember what the product is with Br2? Maybe it involves 2 Brs, right? And I want to identify the intermediate and the mechanism. It's the same thing. This attacks, kicks off a Br. You get this crazy intermediate. that looks like weird with a bromine on it. Anybody remember the name of it? It's a bromine something, IUM. It's a bromonium. And then usually Br minus, we'll just attack that. Usually from the internal position, there's evidence that it attacks on the internal position, opens up, and then you get the product, right? Bromonium. Let's keep going. Our quickie review of chapter 12 stuff. What do we get if we react in alkene with mercury acetate, O8C2, NABH4? Mercury acetate, NABH4. This is a chapter 12 reaction with we had a mechanism in chapter 12 also. And it's, you know, some kind of mercury thing. This was a Markovnikov alcohol formation. So it converted the alkene to a Markovnikov alcohol, just like HBr made a Markovnikov bromide. Okay, and just to review the basic idea of the mechanism and the mechanistic intermediate. The alkene attacks the mercury, kicks off an acetate. And you get a weird thing with a mercury. And if this is a bromonium, this must be a, and then we did a little bit of magic almost to finish this off. But essentially water attacked it, and then the mercury got lost. That's a bromonium. This is a mercuronium. Mercuronium. Okay, that's the name of this funny thing. Essentially, water attacks it the same way that bromine attacked. And then a couple steps. You got the Markovnikov product, right? Okay. Again, chapter 12, I'm not going to really go through more detail, but I'm just reviewing this because it'll help us with the alkyne stuff. Let's keep going. A couple more chapter 12 reactions to review. There was also an Antimarkovnikov reaction. What does that mean? Markovnikov puts things on the more substituted side. Antimarkovnikov puts things on the less substituted side, right? One of them was, okay, that's a benzene. Anybody remember the reagent that does this? It's Antimarkovnikov. It's not HBr by itself. It was HBr peroxides. So the peroxides is kind of an additive, peroxides, and that gave you a weird radical mechanism, radical mech. We'll review that mechanism for the alkynes, but it's essentially it's a different mechanism that involves HBr and something called a peroxide. Any other Antimarkovnikov you may have forgotten, but we did review these on that review sheet. pH again is benzene, so this is basically drawing a benzene. The other one was BH3, H2O2, NaOH. This was essentially the opposite of the mercury thing that we just saw. This is, and it makes an alcohol. So it's an anti-Markovnikov bromide or an anti-Markovnikov alcohol. I'm going to skip this mechanism. It was a concerted syn addition. Of boron, and that's kind of how it attaches to the less substituted side. We'll see it again for the alkynes. Cool. Okay. Anything else? Name of the boron reaction. My abbreviation, because boron, it's a boron oxidation thing. I call this HBOX, which is hydroboration oxidation. Hydroboration oxidation. That's my mark abbreviation for this. Going back to the last page real quick, the mercury thing I have an abbreviation for also, which is called omdm. Oxymercuration, demercuration. Oxymercuration, demercuration. And that's just a way abbreviation I give it for it. Oxymercuration, demercuration. And this is hydroboration oxidation. Cool. All right. So that's all chapter 12. Let's show some of these for alkynes now. So we're still on like addition to alkynes. And first one is if you just take an alkyne, miscellaneous alkyne, and we react it with Br2. You can imagine that Br2 gets added, and it does, but it does it twice. So you kind of like, you first get a addition product where you've added one Br, and then it does it again. Again, AgAin again. So then your final product has 4 bromines. Isn't that weird? 4 bromines. So it attaches once, it attaches twice. That's your final product. Okay, so how does it work? Any guesses? Any guesses? If based on what we learned about alkenes, we'd say, maybe the alkyne attacks the same way, and it does. It's a little funny to draw these things, so I'm going to try to draw them nice and big for you. But the alkyne attacks, and what does that give you? What was the intermediate for alkenes? Whoops. A bromonium. Bromonium, right? The funny 3-member ring with a bromine, right? Now what does Br minus do to that? Oh, I'm sorry, I missed something. There's a double bond here because we had a triple bond and then one of the bonds went away. So don't forget that triple bond goes to a double bond, all right? Triple bond goes to a double bond, all right? Okay. So Br minus now just attacks this thing. And we'll just attack from the back. And what that gives you is essentially the first intermediate. You know, it just opens up and you get a dibromide. Now we're going to do it again. And this is where it gets a little funny to draw, so I'll do my best. Alkene attacks again. Well, what does that look like? Now you got your 2 Brs originally, and you got a third Br that's bridged. Isn't that weird? So you went from, here's a bromonium, this is like another bromonium, and then it just does it again. Br minus. Opens it up. And you got your product, the tetrabromo thing, right? Okay, so that was a nice reaction. It kind of extends from what we know about alkenes. So next one. And all these are, the recordings are online, will be online, and also the notes will be made into a PDF file. Okay, now we're going to go on to specifically Markovnikov reactions. Markovnikov. For alkynes. Okay, so first one is hydrobromination. That means it's hydrobromination, probably. What if there's only one molecule of Br2? Yeah, it probably would stop halfway. For us, we're not going to consider that, though. We're just going to assume always excess Br2. But yeah, I mean, you can imagine it might stop halfway to the dibromide. Okay, so hydrobromination probably implies hydrogen bromide, right? Hydrobromination. So this is going to be considered a Markovnikov reaction. We're going to assume HBr excess. And essentially what's going to happen is you're going to get 2 bromines on one of the sides. So that's kind of why we were going to call it Markovnikov. And it's going to be similar in concept to HBr addition to an alkene. So what happens? I'm just going to have the alkyne attack HBr, just like alkene attacked HBr. You get this kind of intermediate with a funny intermediate with a carbocation. That's a carbocation, a plus charge thing. Okay, and then Br minus attacks that. Br minus attacks the carbocation, just like it would attack the carbocation on a alkene reaction. So Br minus attacks the carbocation. What does that give you? Something that looks like this. The stereochemistry is not clear. It might be cis, it might be trans. That's irrelevant. But the thing is, this will react again. This alkene will react again now. I'm going to kind of go downward to make it nice and big, HBr. And it'll do this to make the carbocation where the Br is. For an interesting reason. Let's see what it is, what it does, and we'll talk about it. All right. So it's going to do the same exact thing. But the question would be, where is the carbocation going to be? Well, we know where it's going to be. I mean, if we look at the product, we know it has to be where the Br is. But there's a cool reason for that. So now we have to, sorry, let's draw it nice and clearly. We have 2 H's now, right? Okay, so this is what I think is the, let's draw it larger even. Okay, it's this, right? So this is the intermediate, and we're going to see it gives us this product. But why does it do this? And why doesn't it put the plus charge on the other side? This happens to be very stable. That's why. This actually has an additional resonance structure. Remember resonance? How it explains stability? Because this has got 3 lone pairs, right? It turns out that if the plus charge is here, Br can actually stabilize it. Isn't that cool? Br can actually stabilize the carbocation and give it different resonance structure, because resonance is a stabilizing thing. What does it look like when Br does this? Well, it looks like HH double bond Br. Is that crazy or what? Look at that weird thing we just made. It's a Br with a plus charge, because the Br is donating its lone pair. Now the Br has a plus charge on it. And that is why it ultimately gives this product, because where the plus charge is actually kind of stabilized. How do we finish off the reaction then? Now Br minus just attacks this. So Br minus now, we have more Br minus, it'll just attack this resonance structure and give the final product. Circle lone pair, attack, kick the electrons onto the Br. And we got the final product. Isn't that cool? So that's why we get a Markovnikov type product where both Brs are on the same place. And that is the product here. Okay, so that's an example of a Markovnikov addition to a alkyne. The dihydrobromination of an alkyne. Now you can stop it also at this intermediate point if you use less HBr, not excess. So you could actually stop it at the mono addition point. But usually people just go all the way to the end here. All right, good. So we're still on 8, which is these Markovnikov reactions. B is going to be omdm. Remember that? omdm. What's the M? Why doesn't the Br just attack the carbocation? Yeah. Somebody asked, why didn't the Br just attack the carbocation? Yeah, it could do that too. It's just when you draw the resonance, there's two resonance structures, you can attack either one of them. I was just pointing out that it is especially stable if the plus charge is there. So yeah, so you could totally attack the first resonance structure. All right, omdm. What's the M stand for? Metal? Which metal is it? omdm. Mercury. All right, good. So this is the basic idea. omdm is oxymercuration, demercuration. Basic idea. Alkyne. Now, so a couple differences from alkenes. First, it doesn't make an alcohol, it makes a ketone. So we're going to make a ketone. Remember with alkenes, it made an alcohol, a Markovnikov alcohol. Alkynes don't make a ketone. That's one difference. Also, remember when we had alkenes, it was mercury acetate, right? HgOAC2. Alkynes will be a different reagent, and it's called mercury sulfate. Mercury sulfate, HgSO4, and H3O+. Sometimes people just write HgSO4 and then H2SO4, which is sulfuric acid. So you could do, but it's essentially acid, H3O+. Okay, so that's the basic idea. Let's show the mechanism now. Big thing though is you get a Markovnikov product as a ketone. So for the mechanism, I'm going to redraw the alkyne. I'm going to redraw the mercury sulfate, HgSO4, slightly different now. I'm going to say Hg2+, Hg2+, mercury 2+, yeah. And I'm going to draw the sulfate, which is SO4. I'm going to draw that slightly different. I'm going to say O minus, S, and then we have two double bond O's. See how that is essentially HgSO4. I just drew it kind of ionically. All right, it's going to help us with the mechanism. All right. Oh yeah, what's the other difference from alkenes? Remember with alkenes, you also had a NABH4 step. Well, you don't have that for the alkyne version of this. It's really just this and acid. It's for some interesting reasons. Okay, what's the final product? It's a ketone. Cool. Okay, so what's the mechanism? What did the alkene version of this do? Alkene would attack the mercury and make a mercuronium, right? That's 2 plus up top, sorry. Okay, and alkynes will do the same thing. So it's essentially the alkyne attacks the mercury. And forms, what was it called? A mercuronium, right? So now we have to just redraw the mercuronium for this one. So we still got the H from the end of the, because there was an H at the end of the alkyne. And now it's like, it's drawn a little funny. It's like dot, 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 HG, dot, 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 dot. And then we have O, SO3 minus on the end. And a plus charge on mercury. That is the funny looking mercuronium that you get for alkynes. The mercuronium looks a little different, okay? The big thing though is it acts like a secondary carbocation. Because it did the same exact thing for alkenes. And that's why it'll be Markovnikov. Acts like a secondary carbocation means that when we have water, which is in the mixture, where is water going to attack? The secondary position or the primary position? It's actually going to attack this secondary kind of middle position. And you see that, that's where the oxygen ends up. So it would make sense that the water would attack the secondary position. So I'm going to just go ahead and attack right there. Okay, so the water attacks the secondary position, kicks the electrons onto the mercury. And what do we get? Water is attached now. That's water attached, right? With a plus charge. And we got our mercury thing on the next door carbon. I'm just going to label that thing that is on there as X. X means the sulfate thing. It's just an abbreviation. All right, so we cool? We essentially opened it up, and now we have water attached, and we have mercury X on there. The next step is just loss of a proton. So water takes the proton, kicks electrons onto the OH. So water takes that extra proton. Right? We cool? So water is, now it's OH, right? Okay. OH. Okay. The next thing, I'm going to call magic. Just because it's not that critical. But this is where the mercury falls off. The mercury is just going to fall off. I have a cool mechanism for it, but we're not going to get into that today or in this course at all. I'm just going to assume mercury gets knocked off, and that's okay. It's a complicated mechanism, and it's a little beyond our level right now. Now we got that, all right? And what's the final product? It's the ketone, right? All right, we cool so far? So it's just a couple steps. Make the mercuronium, lose a proton, lose the mercury. We have this thing. This thing is called an enol. Why is it called an enol? Because it's an alkene with an alcohol on it, right? So this thing will just equilibrate to the final product. Now this actually you will learn, but this is later in the course. It's chapter 18. Chapter 18, so we're not going to worry about the mechanism of that right now. It's just a concept called tautomerism. That's really cool. It's just, we're not there yet. Tautomerism, chapter 18, if you want to read ahead about it, but you don't have to. Right now, this is the critical parts of the mechanism. Make the mercuronium, water attacks, take off a proton, and magically demercurate, lose the mercury, and then it tautomerizes. Okay, cool. Great. So that's the oxymercuration reaction, and the final product is a ketone. Final product is a ketone. So we're still in B, omdm, oxymercuration, demercuration. Let's just show a real example of this. What if I have this alkyne, dialkyne, and I react it with HgSO4, H2SO4. Again, the H2SO4 is the same as H3O+. What's the product? We'll assume excess. So this molecule, two alkynes, gets converted to two ketones. Right? That's what we just showed, is that it's Markovnikov and the alkynes get converted to ketones. Let's just think about a synthesis problem that would involve this reaction. It's a synthesis example. What if I have a ketone and I want to convert it to hydroxy group with another ketone? How could we do that? I mean, obviously we're attaching something. What's the thing that's getting attached? This is the thing that's getting attached, right? That's that piece, that 2-carbon piece got attached. And how could we do that? Maybe through alkyne chemistry. I'll fill in the pieces and you can do the reagents. But we can just attach a 2-carbon alkyne, right? And then later convert the alkyne to a ketone, right? Attach a 2-carbon alkyne. Imagine this being an alkyne. And then we know how to convert a alkyne to a ketone using HgSO4. So I could imagine, couldn't I just do that? And how do we do that? We'll just attach, you know, a 2-carbon alkyne as a nucleophile. And then now we know how to do this, just the mercury thing, right? HgSO4, H2SO4. So yeah, that's a cool example of combining a, you know, alkyne attack with a oxymercuration demercuration reaction. All right, good. Number 9. So we did Markovnikov, and what's the opposite of Markovnikov? Antimarkovnikov. Addition, 2 alkynes. Antimarkovnikov. So these will be analogous to the Antimarkovnikov reactions of alkenes. Okay, first one. Radical addition of HBr. So we use peroxides. Remember that thing? HBr peroxides. So let's just show it, and then I'll show a mechanism for it. Usually this only does a single addition, so not like a double addition. So HBr peroxides. By peroxides, we usually mean ditertbutyl peroxide. So it's tertbutyl, the little cross thing. Oxygen, oxygen, tertbutyl. All right. So this is what we mean by peroxides. So you get kind of a mixture of cis and trans alkenes. That's trans. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons. You probably get a mixture of the cis also. 1, 2, 3, 4. 1, 2, 3, 4. Okay, there's 5. So it's probably a mixture of cis and trans. And it's Antimarkovnikov. Why is it Antimarkovnikov? Because the Br goes on the end, right? All right. So how does that work? This is exactly the same as Organic 1 in Chapter 12. I'm going to review the mechanism, though. All right, so the way I do it, I'm going to show this a series of steps. Rather than, I'm just going to list them like in order. So what's step 1 is called initiation 1. We'll also have initiation 2 and more stuff. So initiation 1 means I have ditertbutyl peroxide, and I'm going to draw Fishhook. So that just breaks down to make radicals. Initiation 2 will be a kind of a second step of the initiation process that gets this chain reaction started. So initiation 2 is now I draw another one of the tertbutyl radicals, tertbutoxy radicals, and I'm going to react with HBr. And this is going to rip off the hydrogen atom and kick off a Br. So it's kind of like Fishhook, Fishhook, Fishhook. 3 fishhooks. So it's essentially going to rip off the hydrogen and create a Br dot. Alcohol, Br dot. All right, we cool? All right, nice. Now we have Br dot, and that's the whole point of initiation, is to create Br dot. Okay, so now we have propagation 1. So propagation 1, what we're going to do is take that Br dot. I'm going to draw my alkyne now. 5-carbon alkyne. 5-carbon alkyne, right? 1, 2, 3, 4, 5. Br dot. So this is exactly also the same as alkenes. When radicals attack either alkenes and alkynes, it does so from the end, because that'll create a more stable radical in the middle of the molecule, like a secondary radical here. So that's why it's Antimarkovnikov. So Br dot now does 3 fishhooks. There's Fishhook 1, Fishhook 2, Fishhook 1, Fishhook 2, and then Fishhook 3 puts it onto a new radical onto the carbon. So the bromine gets attached at the end, and it creates a new radical inside. Internal radical, right? We already have a hydrogen, and that was there initially. There's always a hydrogen at the end. So this is not, I didn't add the H. The H was already there. I just wasn't drawing it. We cool? Ah, now we see why it's Antimarkovnikov, right? Now propagation 2 has to recreate a new Br dot. You got to keep making Br. You use Br dot up, and you recreate Br dot. So now draw our thing that we made. And it sees HBr, and it says, I want to take that H of HBr. Okay? So now the dot grabs the hydrogen, and that will finish the reaction up. These chain reactions are kind of fun, I think. It's nice how it's kind of a little cycle. That's the final product, right? And Br dot. So that we used up Br dot, and then we recreated Br dot, and it does it in a cycle. All right. There's also something called termination, which I'm going to skip. Termination is all these radical reactions have a termination. It's usually just kind of the opposite of initiation. And I'm going to probably skip that. The book may talk about that. I'll just show one termination just so you have it. I'm going to put it in the corner here. Termination. Termination usually just eats up your Br dot. And the easiest way to eat up your Br dot is just have two Br dots find each other. So Br dot finds a Br dot. And what do? Br dots use Br dot. They make Br2. Okay, so that's the silly one example. There's more termination, but we really don't care about termination here. But you know, every one of these kind of reactions has a termination. And yeah, formation of Br2 would be one of them. So that was a cool reaction. That's the formation, the Antimarkovnikov formation of these hydrobromide alkenes. Okay, very analogous to alkene reactions. All right, I think we have one more reaction. All right, let's see here. So we're still on 9 Antimarkovnikov. And I think we have one more reaction. Okay, what's analogous to omdm? Because omdm made Markovnikov a ketone, right? Antimarkovnikov, the analogous four-letter thing was HBOX. Hydroboration oxidation. So that's the anti-Markovnikov version of this, and it's analogous to alkene stuff. So let's show the example. It does the same thing. It's also going to make an enol the same way, but rather than making a ketone, it's going to make an aldehyde. Because it's going to put the oxygen at the end, which makes it anti-Markovnikov, right? Okay, another difference. Well, step 2 is the same, H2O2, OH minus. Memorizing the reagents, like the detailed reagents, isn't a big deal. But you need to be able to recognize the reagents, because I usually give you a reagent list on the exams, and you'll see that on the sample exam. Okay, but anyway, step 1, that normally it was BH3, right? BH3 and then H2O2, OH minus. This one's a little different though. It's cyclohexane. That's cyclohexane, right? 2 of them, BH. It's a little different for alkynes. It's cyclohexane 2 BH, right? What would be a good abbreviation for this? If we wanted to abbreviate it, we could say CY2BH. CY2BH is the same thing, cyclohexane. All right. Okay, so what does this do? It's the same exact thing as the alkenes. I'm going to draw my alkyne. All right, and H, B, CY, CY, the CYs are cyclohexanes. It kind of lines up in this way that the cyclohexanes want to be far away from the molecule. That's why it arranges this way. If it flipped the other way, like it flipped over, then the CYs would be bounced around against the R. So this is why it's ultimately anti-Markovnikov. So now we draw some dot, dot, dots, dot, dot, dot. All right, we cool? So this is going to line up and attach on the dot dot dots. So essentially, arrow, arrow. So we have two arrows. You can see the high resolution version on the website later. But it's basically just two arrows, yeah? And now it attaches. All it does is attaches. Now you have an alkene. B, CY, CY, H. With the boron on there, right? The magic step is basically the H2O2 thing converts this to an alcohol. It's not purely magic, and I actually have a beautiful mechanism for this, but it's just not critical for us. If you want to learn that mechanism, I'll tell you in office hours, all right? Okay, so, and what do we call these things? Alkene with an OH. We had a name for it, right? 4 letters. Anybody know? 4-letter thing. Alkene, alcohol, enol. Not diol. Enol. Yeah, diol would be 2 alcohols. This is 1 alcohol. Anyway, and what do we know that they do? It's a weird verb, tautomerism, or tautomerism. So it's an equilibrium, and this is chapter 18. Cool reaction that we'll address later. Basically converts the enol to this alternate tautomeric form, the aldehyde. Okay, cool. So this is again, that concept, which will be chapter 18, is called enol-keto tautomerism. And it's chapter 18. All right, so now we know the mechanism of this hydroboration oxidation. Is it Markovnikov or Antimarkovnikov? Antimarkovnikov, okay? Okay. So we're still in anti. We're basically done with the reactions now. Let me show just one of these synthesis problems just to think about. If I have an alkene and I want to convert it to alcohol. Oh, wow, what's that thing? That's an aldehyde. We just learned a way to make aldehydes. Let's do this retrosynthetically, right? How could we attach this aldehyde somehow to an alkene? That's totally weird, right? Like somehow, so if we do this going backwards, it actually all works out. So if where's my squiggly line, right? What thing got attached? Ultimately, it was this piece right here. So squiggly right there, yeah? Put a big question mark here because there's a synthesis problem. How do we, if we just go backwards, what's the intermediate look like? And what are the reagents and stuff? Well, I mean, if we just apply the reaction we just learned, we say, well, I know how to make an aldehyde, you know, a 2-carbon aldehyde piece. It would be from the what? What's the starting material here? It must be an alkyne. Oh yeah. What are the reagents of this funny reaction? Look back on the previous page. 2 steps. CY2BH, dicyclohexylborane, H2O2, NaOH. All right, H2O2, NaOH. Okay, so then it's like that's the last part of the synthesis. We're still not done. We have to do this now. So now I do another squiggly, and I say, well, how do I attach that? Maybe if I take that piece as a nucleophile, you know, attach I go attack something with this piece, and what is it going to be? Is it, you know, what are the three things we know that we can attack? A ketone, an aldehyde, or an epoxide? Ketone, aldehyde, or epoxide? Well, I would probably say if the squiggly is there, the OH is here, it must be an epoxide, right? So let's go backwards. Having fun with retrosynthesis, right? So maybe we can imagine alkynyl anion. It's a good nucleophile, H2O. And maybe, what's the thing going to be here? What did we say? It was a ketone, aldehyde, or epoxide. With the squiggly, one away from the OH, must be an epoxide. Okay. I'll draw the mini mechanism of this, of course, from last lecture. And then it's like, how do we go from an alkene to an epoxide? This is actually borrowing from organic 1, one of the key reactions from organic 1 that you should know. 5 letters, begins with M. 5 letters, begins with M, alkene to epoxide. Anybody remember it? Yep. MCPBA is the beautiful way that converts an alkene to an epoxide. A really fun mechanism that I love teaching in organic 1. But yeah, this is a cool kind of synthesis problem where we combined a little bit of alkene chemistry with a little bit of alkyne chemistry, like the attacking an epoxide, with how do you convert an alkyne to an aldehyde? So somebody said retrosynthesis is the hardest part. I'm going to stop the lecture, but I'll talk about retrosynthesis. So I'm going to hit the stop recording.